Okay, so today we're going to talk about auctions, and this is kind of an interesting topic from a game theory standpoint, but also from a social interaction standpoint in terms of how we buy and trade goods, and it'll give us insight into different types of economic behavior that can take place in social networks. So, an auction can be used in a variety of different settings. Of course, you might be familiar with them from the internet. eBay was tremendously popular for a long time. I'm not sure how much it's being used now. It's been a while since I've been on it, but it was tremendously popular for quite a long time. Fundraisers use auction formats. If you've been to a silent auction, university frequently has them. Or at least from time to time. Livestock certainly gets auctioned off. Art, famously, and storage lockers. If you've watched the TV series Storage Wars, you'll see storage lockers being auctioned off. So there's a simplified version of buyer and seller interaction that can give us insight into more complicated forms of buyer and seller interactions. Several different types of auctions, but the ones we're going to be interested in is a single item for sale with a set of interested buyers. Now, you can have a single item to be purchased from one of multiple sellers. That's a process known as procurement, and we may be interested in looking at that a little bit later on, but for today, we're going to be looking at that single item for sale with a set of interested buyers. And to keep in mind with all of the discussion here, we need to keep account of something called the intrinsic or true value. And basically, that's what each bidder is willing to purchase the item for, but not at a higher price. So different types of auctions, and there are four that are discussed. One is the English auction. These are real time. You're probably familiar with these from like Barrett Jackson. Basically, the price is gradually raised until all but one buyer drops out. There's also Dutch auctions, which are descending bid auctions. And these are also real time, but they start with a really, really high number and they keep dropping it until someone eventually makes a bid, and that's the price it's sold for. First price sealed bid, these are kind of the ones that you see at fundraisers. The bidders submit simultaneous sealed bids, or at least are open simultaneously. The highest bidder wins the object and pays the value of the bid. A second price sealed bid is called a victory auction. These are really interesting. We'll see why. The bidder submit simultaneous sealed bids. The highest bidder still wins the object, but he or she only pays the value of the second bid. So only pays value of the second highest bid. So when are auctions appropriate? Well, they're valuable when we don't know the true value of the object. If we're thinking about known values, X is the value which the seller values the item. Y is the maximum value held by a potential buyer for the item. And we're assuming Y is greater than X. Otherwise, we wouldn't sell it, unless we absolutely had to. In this case, there's a surplus of Y minus X that can be generated from the sale of the item. If we know the true value of all the buyers, we can just put it for sale at the highest one, Y, and we don't actually need an auction. For unknown values, buyers really have independent private values for the item. And another case that can happen is when the buyer buys it and then later intends to resell the item, like you see in the Storage Wars show. And basically the idea is the item goes from someone who values it less, which is X, to someone who values it more, which is Y. So let's take a look at these different types of auction formats. And bidders are going to behave differently depending on the auction format. Descending bid auctions, the seller again starts out at a very, very high price and gradually lowers it until someone accepts a lower bid. We don't really learn anything until that auction is complete, in which case the only thing that we learn is the highest value that a bidder had for it. So that's what we learned. First price auction works similar to the descending bid auctions. B sub I still plays the role of bidder I's bid. We learn the highest value of B sub I, and we kind of get some intermediate information maybe about the distribution by looking at how many people stay in. Ascending bid and second price auctions, the item goes to the highest bidder at a price equal to the second highest bid in those second price or victory auctions. The bidders gradually drop out as the seller steadily raises price. The winner of the auction is the last bidder remaining, and he or she pays the price at which the second to last bidder dropped out. And it doesn't make sense to stay in the auction beyond your true value. And it also doesn't make sense to drop out before your true value. So bidders should stay until the price reaches their true value, what it's worth to you. Bidding one's true value for the item ends up becoming a dominant strategy from a game theory perspective here. And you may be wondering about first price auctions. Bidders in first price auctions will tend to bid lower than their true value and bid lower than they will in the second price auction. In fact, this lowering of bids tends to offset what would otherwise look like a difference in the size of the winning bid. So let's do a little bit more thinking about these second price auctions. Second price auctions are basically the ones where the winner pays the second highest price. And they give us insight into other types of auctions. Now, these are common in selling keyword advertising and other applications. I think you can set them on certain internet auction sites. You can formulate these using game theory. The bidders correspond to the players, and the strategy is the true value to the player, V sub I. If a bid is not the winning bid, then the payoff to a player is zero. You don't get anything. If B sub I is the winning bid and some other B sub J is the second place bid, then the payoff is the value minus the second place bid. Ties usually get resolved by some preassigned order of bidders, and there's a minor difference in that we don't know the strategy or the payoffs that other bidders would get because nobody's going to state their true value in an auction. So again, the dominant strategy with these second price auctions is to bid your true value. If you bid too high, like pictured there with B sub I prime, you pay more than what the item is worth to you, and you end up with an item that you paid too much money for. If you bid too low, you may get the item cheaper, but there's a good chance that you'll lose the auction, particularly if your bid is close to the true value of the item. So truthfulness makes second price auctions very conceptually clean because our bid is going to be exactly what we value the item at. Okay, so first price and all pay auctions, and again, these are going to be somewhat different than the second price, but not much. Again, we set it up similar. The bidders are the players. The strategy is the true value to the player, and the payoff, if the B sub I is not the winning bid, then of course you don't get anything, but you don't lose anything either. If B sub I is the winning bid, then the payoff is B sub I minus B sub I. Now, bidding one's true value is no longer dominant since, basically you would get zero if you win because the V sub I is your true value and your bid is B sub I. So you need to shade your bid. With two players, they show that it'll shade down by a factor of 2. With n, it's m minus 1 divided by n times V sub I. So you tend to shade less when there are more players. You have to bid closer to that true value, but not quite at that true value. The result in the last bullet point is derived in section 9.7 if you're interested in taking a look at that. It assumes a uniform distribution of bids, but they also have a more general method that can work with other distributions. Now, the reason we're not going into it for this class is because the derivations of these involve solving differential equations, and we're going to forego those details since this class only assumes CS2 in terms of a requirement. All pay auctions are another format of auction, and basically everyone pays the bid price regardless of whether they win or lose. Political lobbying is an example of this. If you want your congressperson to vote a particular way on a particular bill, you have to pay them, and even if they go the other way, you still end up making that campaign contribution. Another one is design competitions, which is something you may have been involved in during your undergraduate years. You still have to put together that prototype or that design, in order to enter the competition or the auction. So there's a cost involved in that, and maybe time cost or, some small materials for a design competition, but it's still a cost. So, if your cost, the amount of effort that you put into the design competition or the hackathon is not the winning bid, and the payoff is the negative of that investment, because you invested the time and you've got nothing. So it's 0 minus the cost of the time, which is B sub I. If it is the winning bid, then the payoff is the value minus the amount of energy you invested in it. Now, this shares a number of qualitative reasoning features with the first price auction. You want to bid below your true value because you want to make some type of profit, but you got to balance that with your chance to win. So in a design competition, if you put very little effort into it, it's not going to lead you to win. Or if you offer your congressperson a notoriously low campaign contribution in order to vote a particular way, it's probably not going to work, unless they were going to vote that way regardless. Bids will typically be shaded much lower than in the first price auction for these types of all pay auctions. And so far, we haven't been concerned with what the item is worth to others, but that becomes a problem if you intend to resell it. The common eventual value of the object is the amount that it'll generate on resale. Every bidder will have an estimate for it, and if you're reselling them, bidding your true value is definitely not a dominant strategy, and there tends to be a further shading of the bids. The winner gets the item and learns something about its true value from the bidding process based on what other people bid. The winning bid is also likely to be an overestimate, which is something called the winner's curse, and that's common in oil drilling rights and in baseball free agents. So how much can a seller expect to make? Well, assume the value in the bids are on a 0 to 1 interval. Now we can scale that interval to whatever we like by a multiplication. So for first and second price auctions, or actually a linear function, if we didn't want the first one to be 0. For first and second price auctions, the expected value of the seller is n minus 1 divided by n plus 1, where there are n folks that are bidding. The seller's revenue ends up being the same across a broad class of auctions and arbitrarily independent distribution of bidder values when the bidders follow the equilibrium strategies that we discussed earlier. And that's something known as revenue equivalent. So, the auction just format just adds excitement to it. But there are minor differences, but in general, we end up with similar results. So that's it for chapter 9. Thanks so much for watching.